All right, so welcome back, everyone. So today we're going to talk about the diffuse interstellar bands and also about interstellar dust and its composition. So for the diffuse interstellar bands, also called DIBs, they are essentially a whole bunch of absorption transitions in the near-infrared to visible region over here. All right, so as you can see right here, here's the visible spectrum. And then all these little white areas, these are where essentially the absorption lines are for all these DIBs. So they're very, very numerous. But the only problem is we really don't have any idea what these actually are. So they're one of those great mysteries in interstellar chemistry. So these DIBs, there's a whole bunch of absorption features, and they are much broader than you would normally expect from Doppler broadening. So just based upon the temperature of the gas. So what this is basically telling us is that these are probably some short-lived excited states or large molecules. All right, so remember from before, if we're talking about the Heisenberg uncertainty principle, if we have an excited state which has a very short lifetime, its absorption or its energy levels are going to be very, very uncertain, and that's going to lead to a broader absorption feature. And also for dealing with large molecules, these can have many vibrational bands, many close rotational bands, so there can be a lot of overlap there, so that can also lead to a very broad absorption as well. So it could be one or both, or probably some combination of both of these things. Now these are called diffuse, and your first inclination might be because these are only seen in diffuse clouds, but in reality it's because of the broadness of the transition. So because they're so wide, that's why they're called diffuse. It just happens to be by coincidence they also appear in diffuse clouds as well, but the naming is actually because of the width of the lines. That's what this actually comes from. All right, now these diffuse interstellar bands have been known for quite a while. They were discovered over 100 years ago, essentially just taking spectra of different stars, and over 1,200 of these individual lines have been cataloged. So again, there's very numerous. Again, there's probably a lot more of the little tiny ones, but even these large absorption transitions are still fairly numerous. And as we'll see later, only a few of these have been conclusively identified. There's been on and off what some possibilities have been, but very few conclusive identifications. Okay, so what are the DIBs? So these are seen along many different sight lines, and when I say sight lines, I mean between us and a distant star. So that's essentially just whatever intervening material is between there. Now it says here that there's a reasonable correlation with dust extinction. That means that as you get more material between you and the star, the intensity of the DIBs increases. But eventually, when you get to a high enough extinction, in other words, it just levels off. So even though there's like more material between you and the star, it doesn't get any deeper there. And again, these are seen mainly in diffuse clouds. Now, solid-state carriers are generally favored. When I say solid-state, it generally means not necessarily gas phase, but perhaps larger molecules that start having band structures in them and everything. However, it is probably not dust. All right. First of all, the absorption wavelengths are very consistent. This means that, unlike dust, which can have a wide variety of shapes and sizes and compositions, which would lead to, absorption wavelengths being all over the place, these are, completely consistent. So in other words, you look at, one sight line and one like going north, another one going south, another one going east and west, completely different areas, and, the absorption wavelengths are all exactly the same there. Also, there is a lack of emission. So if this was dust, what would happen is you'd absorb some energy, and then you would be emitting some lights probably in the infrared, and there's not like an infrared glow that is also being seen there. All right, and then finally there's also a fine structure that is also present. So right here's a DIB at 5797 angstroms, and as you can see along three completely different stars here, the spectral features match up basically perfectly. These are essentially just kind of like lining up the little mini features that are actually seen inside of there, trying, because this one had the best resolution, just trying to see how these actually correlate between these different stars here. So this really indicates that this is perhaps just one single molecule, and there might be some rotational structure or vibrational structure actually going on inside of here. Yeah, unfortunately, no one actually knows what molecule or molecular ion is actually causing this, but it definitely points to the fact that this must be a certain molecule that is actually doing this, because it is so consistent between all these three different sight lines. So the consensus as of right now is that these are all gas phase molecules. They are probably very large, meaning that the small ones have probably been easily found on Earth, but large ones are much more difficult to get into gas phase, experimentally speaking. So it's very difficult to actually do some measurements on these particular molecules. These are likely carbon-based, and as we'll see in a minute, where that is basically coming from. And it's more likely that a lot of these DIBs are a reservoir for a lot of organic material that's actually out there. All right, and as I said earlier, it's really one of the greatest unsolved mysteries in interstellar chemistry, what is actually going on with these. All right, so I said that these are probably composed of carbon, and the reason for that is a lot of these DIBs correlate very strongly with the amount of carbon that's actually in that same sightline. So right here, this is just saying how much diatomic carbon is between us and these different stars. So these right here, these are just different stars that we're actually looking at. And here at these dotted lines are just a couple of the DIBs that have been observed. As you can see, obviously less carbon, less diatomic carbon on the top, more diatomic carbon on the bottom. So as you go down a lot of these sight lines, as you increase the amount of diatomic carbon there, these lines become progressively bigger and bigger and bigger. So that is a good indication that if there's more diatomic carbon there and the lines are getting bigger, then they probably both of them have carbon in them as well. So that's one piece of evidence that these contain a lot of carbon. Also of interest is that some of the DIBs, again not all of them, correlate pretty well with the atomic hydrogen over here. So here this is the log of the number density of hydrogen, and then this is the log of basically the intensity of a particular DIB. And as you can see, they correlate pretty nicely, about R of 0.994 if we ignore some of these little outliers here. But if we also compare this with diatomic hydrogen, you can see that the correlation basically is really non-existent. So what this kind of tells us is that, again, remember, if you have only monoatomic hydrogen but not a lot of diatomic hydrogen, that's going to be an environment that very easily destroys the diatomic hydrogen. That's why your diatomic hydrogen doesn't correlate very well with molecular clouds. But in the diffuse clouds, there's a lot more atomic hydrogen, not a lot of diatomic hydrogen, so then these DIBs correlate much better there. So again, these are usually found in diffuse clouds, but not named after the diffuse clouds. Basically, we're just searching for common carriers, so what would make sense? Basically, the assumption is that these are gas phase molecules and that the DIBs are some vibronic bands. So right down here is your ground state, the X state. And since space is cold, we're going to be probably starting in the zero vibrational state. And then we're going to be going to some excited state A, which has a whole bunch of vibrational bands. And then each of these vibrational bands is potentially one of the DIBs there. All right, and like I said, low temperature, so everyone's at zero. And the relative intensities are fixed mainly because the Frank-Condon factors, just from the quantum mechanics, determine that. And also, since everything is cold, everything is essentially starting here in the ground state. There's no excited states to really worry about. So therefore, all these transitions should be independent of the temperature and the number amount of molecules that are actually in there. So the ratios should all be fairly constant. All right, so what they did in this little particular experiment was that they looked for DIBs that have tight correlations with intensity. So essentially, we're just going to be looking at the intensity of different DIBs and see which of them correlate very, very nicely. And ideally, what you'd be able to do, unfortunately, this hasn't been done as of yet. If you're able to see one of the DIBs, they correlate very well with each other. You can look for the similar spacing, and therefore you maybe identify the vibronic spectrum, and then from a little bit of detective work, maybe figure out what possible molecule could actually do that. Unfortunately, as far as I know, that hasn't been accomplished as of yet. So not all DIBs are going to correlate very nicely. So here, these are just two DIBs over here, and as you can see, there's basically no correlation. I mean, they're going in the same general direction, but they're not really that nice. Now these are actually, these two DIBs over here were originally hypothesized to be the C7 minus bands. So there was a little controversy back in the 90s when they were trying to identify it. One group came out and said, they did some spectroscopy work and they identified, two absorptions at around 4963 and 6270 that corresponded to C7 minus. Now, it's very unusual to have an anion in interstellar space because it's very easy to knock an electron off. But, maybe there was some stabilization, going on that made the C7 minus to be stable. So, it's a possibility. But basically, it came out and kind of diffuse and said that it wasn't really likely that the C7 minus was actually there. So it was actually fairly easily disproven about a month or so after it was hypothesized. So as you can see, they correlate between these two DIB bands. They don't really correlate that well. So more than likely than not, they're just coincidence. Again, if you're having 1,000 different intensity bands, there's the possibility that just by coincidence you have just the correct spacing that could lead to a false identification. But if the intensities are all over the place, more likely than not, these aren't actually from the same carrier. Now, on the other hand, these two, these look very, very nice. All right, they correlate very well with one another. Unfortunately for this, we do not know what these are actually caused by, but we have an R value here of like 0.985. So these are very, very nicely correlated with one another, and as we'll be seeing in a little bit, an R of like 0.95 in astronomy terms is actually pretty darn good. Now, really, the possibility here is that measurement errors that's actually going on, these could actually be causing a lot of deviations. These could be actually causing most of the deviation that we're actually seeing here. So they basically just did a little simulation just to try to figure out, is this actually possible? So of all the DIBs, so they looked at 1,218 pair of DIBs, and they looked at these in over 40 stars. And essentially, they made a nice little histogram, just comparing, how these things actually correlated. And there's very few, so basically just 19 over here, that had really, really good correlations. Some of these, they might just be coincidences, especially when you start talking, about like 0.8 or below. But some of these over here, they may actually be related. But still, even like if you're like in the 0.9 variety, it's probably more likely just a coincidence rather than just saying, these are actually from the same carrier. So really, most of the strong DIBs, they have distinct carriers. So the weaker ones, they might be starting to get a little bit into the noise, but the strong DIBs, they're basically kind of independent. So it's not like there's just one unique carrier for all the DIBs that are actually out there. So one thing you could do to basically see, are these two signals actually from the same carrier, or even though they correlate very, very nicely with one another, are they statistically different and just happen to be very well correlated just by chance? We can actually do a little bit of a simulation here. So the observed correlation coefficient is 0.986. So basically you can start off, say, okay, well, if these are from the same carrier, we should have perfection over here. And then any of this little noise that we have is really just due to signal variations and limitations of the equipment, shot noise and all that other stuff. So first of all, we're assuming perfection. So in other words, R would equal 1. And then you go and start adding some Gaussian noise on top of this. Basically what you would expect from the limitations of the telescope and everything else. So when you do this, you get about like a 0.996. So that's assumes that you'd have much better correlation than you actually observed. But of course, you want to do not just one trial; you do a whole bunch of trials. But still, even when you do that, you find out that the correlation coefficient for just regular Gaussian noise is basically going to be 0.995 and better. And here we are at 0.986. So that's not too promising. But then if you just say, well, actually, let's just try doubling the noise here instead. And now, when you do that, you get 0.985, which is essentially the same as that. And again, you do 1,000 repeated trials on this, and now you can see that the R coefficients are essentially right in this range. So statistically, this seems to make sense if we are underestimating the errors. Now, what are possible measurement errors when you're actually looking at this, just to kind of get an idea here? So in other words, is that doubling of that error estimate, is that a reasonable assumption, or is it just trying to fiddle with the results to make yourself happy? So some possible errors, there's a finite signal to noise ratio just from the telescope itself. So there's always going to be a little bit of bounciness and stuff on the absolute signal there. There could be some unexpected structure that's actually going on that you may just think, well, there's just a nice little line here, but there could be overlapping lines. So there could be perhaps another DIB that just is coincidentally right on top of there. Also the continuum placement. So in other words, where is the baseline for this? Ideally everything should be a 1 over here for the baseline, but there's some little variations there, and it's basically just trying to find what is the height of Mount Everest, and you're trying to figure out what sea level is. So there's going to be a little bit of variation over there, and exactly like where the 0 mark, or in this case the 1 mark for the intensity actually is. So that can also add a little bit of uncertainty to that. But it also bears in mind that agreement is not always going to be perfect. So right here, there's a CH plus band, the 8X band. So this has been conclusively identified. The 00 and the 10 bands over here. So since they are the same carrier, both starting from the ground state, you would expect them to have perfect correlation. But you do this, and here correlation is 0.985. So that's perfectly consistent with what we saw on the previous slide for those DIBs. So it's more likely than not that they actually have a common carrier between them. But what that is, no one is completely certain with that yet. All right, now one line that has been conclusively identified is the C60+. So C60, of course, is Buckminster fullerene. So this is the ionized version of Buckminster fullerene over here. Now, this is a very, very complicated molecule, and maybe interesting. Like, how can we actually conclusively identify this? We'll get into that in a bit. But basically, what's going on here is, the C60 plus is in its ground state over here, and then once you ionize it, it actually undergoes what's known as Jahn-Teller distortion. So this thing is not going to be nice and spherical soccer ball, but it's actually going to be distorted, and it's actually going to cause a splitting of the energy levels. And over here, essentially, there is a weak transition probability going from the ground state to some of these excited states over here, and then, in other words, the E states and also the A states over here. So there's a weak transition probability for those. And these correlates very nicely with the 9577, the 9632, and also the 9365 and 9428 angstrom DIBs that have been actually seen. So how do we actually, first of all, figure out that C60 plus is actually responsible for these? Well, this a little bit of history here. They first observed the absorption spectrum of the C60 plus in a neon matrix back in 1993. So this right here is the absorption spectrum of that. And here in the blue, you can see one of the DIBs towards HD 183143. Now you'll notice they are pretty close to one another, but they don't exactly line up. And also there's a lot of broadness in the C60 plus line that's in the neon. All right. Now, first of all, this shift is actually caused because the C60 plus in space is obviously in the gas phase, but here this is in the solid phase surrounded by neon atoms. So all those neons are perturbing the electronic structure of the C60 plus. So it's not unusual to see shifts of a couple hundred wave numbers actually going on in the visible region for this. So this is not completely unexpected. It's seen in many, many other molecules, and also the broadening that's going on here too is also caused because we are in a neon matrix there. So this, first of all, when they realized, well, there's a very similar spacing here, there's a very similar spacing here, they seem to have similar intensities. So it was likely that there was possibly the C60 plus, but until they could actually get a gas phase measurement of the C60 plus, no one could make a definitive identification of that yet. So what we needed to do was somehow have C60 plus in the gas phase. So since as you should know, C60 plus is going to be a is going to be a solid. So you need to heat it up by quite a bit. And in fact, you need to get it to around like 340 degrees Celsius until you get like enough of it to actually sublime that you get a good enough fraction in the gas phase here. And once you get your C60 in the gas phase, you can go whack it with some 65 electron volt electrons, just like you do in a mass spec, and then that forms your C60 plus. And then you basically put this through a mass spec, so you can just sort out the ions you're only interested in, and then you can go and store that in an ion trap. Now at this point, we need to worry about trying to vibrationally cool the C60 plus, because remember, you heated this up to 340 degrees Celsius. This molecule is going to be very vibrationally excited. Not to mention that you just whacked it with an electron over here. So it's going to be in a highly vibrationally excited state. So you want to get this down to the ground state. So you put a little bit of helium in there, and then as it's bombarded by the helium, the helium bumps into the C60 plus, takes away a little bit of that energy as it bounces off, and it works on actually cooling the C60 plus. And eventually, what will happen is you'll form a C60 plus helium complex. So finally, one of the heliums essentially just sticks to the surface of the C60 plus. And then you have this in your ion trap. So you have your C60 plus helium complex basically floating around. You have a laser, which you tune over wavelength. And then you just monitor how many of the C60 helium complexes actually make it through. So if there's an absorption here, this is going to excite the C60 plus to an excited state. And then that excited state is now going to have enough energy to kick off the weakly bound helium. And now it's going to have a different mass, and therefore it is going to not actually be stored in that ion trap anymore. It's going to basically leave. If you don't have an absorption, that light is not going to be absorbed, and the complex is going to pass through. So essentially what you're doing is you're looking for the disappearance of this complex, and that's going to correspond to an absorption. And this has also been done for other molecules as well. So this is a complicated but well-researched technique. So here are the results. So here's that carbon-60 in the neon matrix that was observed from last slide. And then over here, this is the C60 plus in the helium complex at 4 Kelvin in the ion trap. So as you can see, first of all, the transitions have moved this way. So that's in the correct direction. So that's always an encouraging sign. Also, all these things basically correlate very nicely. Also, now the transitions are very, very narrow. So this tells us that we have vibrationally cool molecular ions, so that's very encouraging. And in general, shifts from the neon are 100 150 wave numbers, give or take. But the shifts on the helium, because there's still going to be some perturbation from the helium atom there, these are generally less than 1 wave number, which in the context of the astronomical observations are very, very small. So we really don't have to worry about that too much there. But then once we take this spectrum over here and then overlay it with the DIB spectrum, you can see that these two lines match up perfectly well. And from the cross section over here, you can kind of work out exactly what the how many C60 plus you would actually need to have an absorption of this particular depth over here. And it works out that about 0.3 to 0.9% of all carbon would have to be in the form of C60 plus to basically account for the strength of these DIB lines there. So it's actually a remarkable percentage seems to be in the form of these fullerenes there. Now, carbon 60 has the special properties. They've also looked, I think, at like C70 as well. So far, there hasn't been any matchup with the DIB lines, but they're definitely looking to see if there's any other fullerenes that could potentially also be potential DIBs as well. Okay, so we said that DIBs are dust. But what is dust, and what information can we get spectroscopically from the dust to actually tell us about what's actually going on here? So unlike molecules, dust does not have unique spectral length. Like I said earlier, dust can have many compositions, can be many different sizes. So essentially, any ultraviolet and visible absorptions are a continuum. So you're just going to see a broad absorption feature for the dust there. And the energy levels there are just going to be way too close to actually talk about resolving anything there. So, and if there are any spectral features, they are going to be very, very broad, and there's really no unique identification because you're literally talking about thousands to millions of atoms in there. So it's impossible to have a unique identification for these dust particles. So alternatively, we can also ask what is probable, and through some calculations, which I'll discuss a little bit in a few minutes here, we can say that the mass of dust that's out there compared to the mass of hydrogen is about 0.83%. So dust is a relatively large fraction of the matter that is actually out there. And I'll talk a little bit about how they actually came to this conclusion over there. Other things are that certain elements are depleted, and therefore if their abundances are less, they are probably in the form of these dust grains. Okay, so as for the dust properties, observations are going to give us some constraints. So first of all, there is a wavelength-dependent attenuation that's going on. So that means that as the starlight is passing through the dust, it is not attenuated uniformly across all wavelengths. Certain wavelengths are going to be more strongly absorbed and scattered. Others are going to pass basically all the way through there. So longer wavelengths tend to go through no problem. Shorter wavelengths, they tend to get scattered around. There's also a polarization dependence on the attenuation as well. So depending on how the light is aligned with the dust grains, determines how well it is attenuated. We can also look at scattered light in reflection nebula. We can also look at the thermal emission from the dust. So as the dust absorbs energy, it has to be emitting some infrared radiation as well. So that's going to be some thermal emission right there. You can also look at, as X-rays are interacting with the dust, this is also going to cause some small angle scattering. So you can kind of see little halos around where the dust would normally be. And there's also luminescence from illuminated dust. And this is so-called extended red emission as well. Also, presolar grains have been preserved in meteorites. So it's a good way to actually have a physical sample to observe. Also, the diatomic hydrogen abundance. We talked about this in the before times when hydrogen can only form as it's interacting by the two atoms coming out of dust grain and then coming together to form a diatomic molecule, and we don't actually have H2 forming by two hydrogen atoms actually colliding. And we can also look at the temperature of atomic hydrogen and diatomic hydrogens that's heated as the photoelectrons are emitted from the dust grains. Okay, so as I said, there is a wavelength-dependent attenuation going on here. So right here, this is the reciprocal wavelength, so that's in other words proportional to the energy of the light. Here, as we have long wavelengths, in other words low energy, there's very little attenuation going on. As we reach higher and higher energies, smaller wavelengths, there is more and more attenuation actually going on here. Now the attenuation here, this is just given by the magnitude, so that's basically just, again, the base 10 log of the ratio of our fluxes. We stop over here. This energy is right around 13.6 eV. Again, once you get above that, that's when your ionization of hydrogen starts taking over, and it's really not going to correlate very well with the dust because that extra features there. So if we're below the 13.6 eV, this is pretty much just all going to be absorptions from or scattering from the dust that's actually there. All right. So here, your stars are actually. So one thing about the dust is that this is going to cause reddening of the stars, and this is why as the light passes through more dust material, the stars are actually reddened because blue light is going to be more and more attenuated over here. So in this case, these are higher wavelengths. These are going to be scattered and absorbed more. Down here, the red light is basically not going to be scattered at all, so that comes out very cleanly. So that's why if you're actually observing, let's say, stars in the center of the Milky Way or any galaxy, if you're doing this in the visible regions, you basically can't resolve anything because all that dust that's in there makes all the starlight just completely scattered away. It's kind of like it's literally looking through clouds. You can't see anything. But if you're looking in the infrared region, that starlight is really not being scattered as much. So essentially you have a clean line of sight between you and the star, so you can actually observe individual stars near the galactic center, even though there's a lot of dust, because the dust doesn't scatter very well there. And it's the same reason why the sky is blue, the sunsets are red. The longer wavelengths don't get scattered quite as efficiently, so that's why the sunsets are red. But we see the blue scattered light, of course, during the daytime, because that's the light that actually does make it all the way through. So from the previous slide, we saw that as the wavelength becomes smaller, the attenuation just keeps on increasing. And what we'd actually expect that if your dust was large relative to the wavelength, then your extinction cross-section basically would be independent of the wavelength. So since we don't see any leveling off there, that basically tells us that the dust grains must be smaller than the wavelengths that we're actually looking at. So therefore, small grains have to make appreciable contributions to that. Now, what do I mean by small? So from optics, small basically would mean it's like 2 pi times the radius of the grain divided by the wavelength is less than 1. So essentially, when we're talking about small, we mean that the size of the grain is smaller than the wavelength, generally speaking. All right. So from our wavelength considerations, this mean that our grains have to have radiuses less than like 0.15 microns or so. Now that aromatic feature that we saw over here, this seems to be due to some sp2 carbon pi-pi star transitions, and these are probably going to be some polyaromatic hydrocarbons, or PAHs. So we'll talk a little bit more about these later on today. Now I mentioned also polarization. So what they have noticed is that the polarization increases for stars that are more reddened. So in other words, the more dust that is actually there, the starlight is actually more polarized. Now, starlight, when it's coming out of the star, is initially unpolarized, but as it scatters off of dust grains, it picks up some polarization. All right. Now, what is noticed is that if you're looking at stars in the same direction, they're going to have similar polarization orientations. So we can actually look here. These are actually about 2,000 some stars that are in the area, and essentially you're just looking at what is the polarization of the light from these individual stars. Okay, so the length of the line here basically tells us the amount of polarization. So if it's like really long, it's like a 3% excess polarization. So it's a small amount, but you basically expect nothing. And what you can kind of see is that stars in the same area are kind of like the polarizations are essentially aligned. So you can see like right here, they're all kind of going in the same direction. Over here, they're kind of going same direction-ish. Here, they're kind of going the same direction-ish. And then, out here, there's not quite as much polarization. But along here, this is actually where there's a lot of dust. So this is, again, the galactic latitude. So at 0, this is looking through the center of the galaxy, basically, or along the galactic disk. So there's a lot more dust there. And you can see that, there's a lot more polarization because of that dust. So as we said, there's more reddened is going to be more polarized. Also, you can see that, like I said, these things are aligned. So what's most likely happening here is that there's interstellar magnetic fields, and by some mechanism, this aligns the dust grains. Now, probably what's going on is the dust probably isn't neutral, so there's going to be a little bit of a charge on there, and of course, moving things in charge and how they respond to magnetic fields. So these things are probably aligning along the magnetic fields here, and then once the light comes along, it preferentially interacts with the material and winds up actually polarizing some of the light there. So this is also kind of giving an idea about what sides the dust grains actually have to be here. And to get the results of the polarization that we just saw, the grains would need to be aligned with the shortest axis parallel to the magnetic field. And the dust particles themselves are probably going to be spinning because they're constantly being impacted by atoms and molecules and other dust particles. So that's going to give them a little bit of angular momentum. And the dust particles again are most likely going to be charged because they're being interacted with radiation. So charged things in magnetic fields, they're going to be spinning there. So the way this orients itself is with the shortest axis parallel to the magnetic field. One observation that is made is that the polarization declines as in the ultraviolet as the extinction increases. So as we saw, the extinction increases as you get to shorter and shorter wavelengths, but the percent of polarization actually decreases as you get to the shorter wavelengths. So what's seen is that if you're talking about in the visible wavelengths, so around 550 nanometers, this has a large contribution from grains that have sizes around 100 nanometers. And essentially what this is implying is that the grains are non-spherical and they are aligned with the magnetic field. However, as you get to wavelengths shorter than 300 nanometers, so this is going to be in the ultraviolet region, there is going to be a large contribution of grains with sizes around 50 nanometers. So the possibility here is that either the grains are spherical, which they're probably not, because if they're going to be non-spherical up here, why would they necessarily be spherical down here? So probably they're going to be non-spherical as well, but more likely is that they're going to be minimally aligned. And it's possibility the possibility is that since the grains are just so small, they don't align as well with the magnetic field as grains that are actually going to be larger over here. Okay, next up we'll be looking at what scattered light could actually tell us. So in this case, we would have a bright star which is near a cloud of gas. So it's just like looking up at a cloud on a sunny day. The cloud is being illuminated because, of course, it is scattering light from the sun. So the light that's coming off the star is not going to be bright enough and high enough in energy to ionize the gas. So this is not going to be emission. That's a completely different process. All that's going on here is that light from the star is essentially just scattering off of dust in a nearby cloud. All right. Now, how do we know that this light is actually being scattered from a star and not just being excited and undergoing emission, and the light is coming from the gas inside the nebula itself? Well, we can again look at the spectral features, and what you notice is that the nebula has spectral features in common with the star, which is really, really close by, and not independent of that. So since it has the spectral features of the star, therefore it must be light that is being scattered by that star. And one thing that you want to look at here is the light that is coming from the cloud versus the estimated brightness of the starlight. So you can basically say, well, how much it is glowing is going to tell you important properties about the dust that's actually inside of there. Okay, so first of all, we're going to look here at the dust albedo. And albedo is the ratio of the scattering and extinction cross-sections. And scattering, of course, is just light that is scattered off of the dust grains. Extinction is the scattering plus absorption. So it's the ratio between those two, and essentially it's just how shiny the dust particles actually are. What we see is that the dust albedo is around 0.5. So in that case, that means that your absorption and scattering cross sections are about equal for the dust grains. All right, the other thing that we can look at is the angle of scattering. So here, this is like the average cosine of theta is about 0.5, so that gives you an angle theta of about 60 degrees or so. And for this to actually work, this basically implies a forward scattering that's occurring here, and that the size of your dust particles are going to be around 100 nanometers. So as you can see, all these things that we're looking at, the polarization, the scattering, the attenuation, all these things are coming out consistent on what the size of your dust particles are and everything else like that. Now, if we were actually dominated by Rayleigh scattering, in this case, the cosine theta would be about 0, and the particles would be much, much smaller than the wavelength that we're talking about. And of course, this is why the sky is blue. This is in fact dominated by Rayleigh scattering, and that's because Rayleigh scattering in the Earth's atmosphere, at least, is due to the oxygen and nitrogen molecules that are floating around. Of course, they are much smaller than the visible light that we actually see, so therefore Rayleigh scattering dominates. But if we're talking about a lot of dust, these dust particles are going to be at least comparable-ish to the wavelength of the light that you're talking about, and therefore we're going to be having this regular scattering actually coming out here. All right, so here's an example of a reflection nebula which has some scattered light in it. So this is actually the Trifid Nebula. It's about 4,100 light years away, 21 light years across, and this actually has 3 different types of nebula all in one. So back here, we can see the reflection nebula, and again, just kind of like the blue sky, this is blue because again, it's going to be scattering the higher wavelengths, or the the smaller wavelengths of light, the higher energy light over here. So it's scattering the bluer light preferentially. So that's of course why this looks a little bit on the bluish side. Down here we have this reddish emission nebula over here, and again that's probably emitting a lot in the hydrogen, is causing usually the reddish color. And over here we have these dark streaks, which are dense clouds, where the nebula is starting to collapse. So in this region over here, we basically have three different types of nebula right in one. All right, here's just looking at some data here. So over on this side, we're looking here at the albedo, and over here we're looking at the average cosine of theta. And this again is versus 1 over the wavelength. Down here, this would be your long wavelengths. Up here would be your short wavelengths. And then we have these three different lines which are going here. These are basically the theoretical values for the extinction curves that we would basically be expecting for different densities. Over here, they basically all come out pretty close to one another, and then of course all these little circles and squares and everything. These are actual data from different galactic sources and whatnot. So you can see for the most part, they kind of agree with the curves that we have. So first of all, the diffuse galactic light. This is essentially looking at light scattered off of the diffuse clouds that are in space. Here we have basically clouds. These are like dense molecular clouds. This is kind of dominated over here by the longer wavelengths because for the most part the shorter wavelengths just don't make it through there. Here we have a reflection nebula like that blue one we just saw. As you can see, we actually have a little bit enhancement over here in the shorter wavelengths because this right here is going to be that's going to be easily scattered by the reflection nebula. So we do see a little bit of enhancement there. And as for the angles, you can see that for the most part these are mostly forward scattering and stuff, and they come out pretty close to what our theoretical values actually are. And by the way, the cosine theta, this is called an asymmetry factor. Again, it's just letting you know, like, what, is the light being scattered uniformly, or is it, being scattered preferentially in one direction? And that's what's basically it's saying right here. All right, so the next one up here is luminescence. So there's actually a peak in the 6,000 to 8,000 nanometer region, and the light that's coming out in this region is actually more than you would normally get from just scattering alone. Now, what is actually doing this? It has not been identified as of yet. Some candidates are possibly PAHs, which are polyaromatic hydrocarbons. We'll talk a little bit more about that today here. Or possibly the PAH cations. That's also another possibility. Now, the light that's coming out of here, we said this is more than scattering alone, so probably what's going on is you get your PAH, it's getting hit by, let's say, ultraviolet radiation, and then it relaxes to a lower energy state, and then goes and emits some more radiation over here in the visible. So that's why, that's a possible candidate. So it's kind of like a fluorescence, phosphorescence thing going on. We'd just generally call that luminescence was what we're seeing. All right, now as for the dust, of course, it can also have infrared emission. So what's going on here is that the dust is heated by starlight, and then since it's acts as a blackbody emitter, it will cool by emitting infrared radiation. And this will add, basically additional constraints on the size and composition. There's also a large dip and some emission features at short wavelengths, and we'll look at a little bit of that in a minute here. So right here we have essentially an all-sky survey of the dust. So this is at 100 microns, and this is actually after they subtract all emission from dust in our own solar system. Now the bright parts right here, this obviously is areas with more dust. This of course corresponds to the galactic disk that you're actually looking at over here. In the southern parts, this is essentially where your large and small magellanic clouds are, and then there's basically just little bright sources here and there and stuff. Okay, so here is essentially how the emission from the dust actually goes. So it's not a nice curve like you might expect from blackbody radiation. So over here, this is the Cosmic Microwave Background Explorer, COBE, Far Infrared Absolute Spectrometer. And this basically does follow blackbody radiation. But then once you start getting into this region over here, you can see that there's quite significant dips, and this kind of puts some constraints on essentially the size of the particles that are actually doing this. And then we start having some structure out here as well. The total power here at the lowest wavelengths, this is basically about 65%. This is about 14% over here in the middle, and then up here on the top, this is around 21%. And this is where it's starting to get to shorter and shorter wavelengths. Down here, this is the long wavelengths over on this side. All right, so then what we can do is essentially just model what that emission spectra would actually look like using silicates, also graphites, and the PAHs, And this is the interstellar radiation field, basically just looking at the intensity from either like 0.1 to about 10,000, whatever, versus our local values. And this is essentially fits fairly well with the previous slide that we just saw, although for whatever reason, the axes go the different direction over here, because this is 1 to 1,000, whoops, and this one goes basically, here's 1,000 down to 1. So it's kind of like reversed, but as you can see, you got these features over here, and then it gradually goes down on this side, and this basically just depends upon how much, because when you get to this point right here, this essentially is just the black body radiation coming off. Now, as for all the details about what's actually going into there, it's a little bit above my pay grade what's actually going on with these. So basically, they're modeling the temperature of the grains, the radiation that's incident on the grains. You have to also look at this stochastically as well, because the light is very, very dim and the grains are very, very small. So it's not a continuous bathing in light. In fact, the light that's actually coming on is kind of stochastic in nature. So it's basically little photons coming occasionally, and then you have to kind of model how that will interact with the dust grain over time. So, but you can, like I said, you can basically model these things fairly accurately. So I mentioned a few minutes ago here, how much dust is actually there. Again, this is a little bit above where we want to start trying to explain this thing here. But basically, there's something called the per cell limit, which is the lower limit on dust volume. And essentially what this is doing, just to be overly simplifying here, is it looks at these Kramer's coordinating relations. And essentially, these are looking at how a dielectric medium, which is going to be the dust, responds to the electromagnetic field, which is, of course, the light. So essentially what we're doing is we're saying, well, if we have some dust particles up there. They are dielectric because they're not normally conductive, and that's usually going to be the case if we're talking about things like silicates and non-conductors. So we're basically just seeing, well, how is light normally going to interact with those, and from those observations, basically this is where we get our 0.0083 times the mass of the hydrogen. And this is assuming that the dust has a density typical of usual silicates, about 3 grams per cubic centimeter. If the dust is a little bit denser, that might change it around. But just taking your average dust and interstellar material that you normally would find. So that's where that kind of comes from. But I don't want to get into any more detail over that. All right, so what is the dust actually composed of? Well, hydrogen can't contribute appreciably to the dust mass, because even if you were to, say, make polyethylene, you would still be talking 86% by weight carbon. So hydrogen is not going to be that much, and especially when you're talking about metals and everything. So it's not going to be that much there. So what has been inferred is about 2/3 of the carbon and more than 90% of the magnesium, silicon, and iron are in the dust. So the way they figured this out was they looked at the absorptions from the starlight here, and if there was no depletion actually going on, all the elements would be right on this dotted line up here. But as the elements are being depleted, meaning that they're going onto dust grains, so therefore they're not available to be seen, they're now going to be depleted over here. And you can see there's a general trend as we look over here, comparing this to the condensation temperature. So this condensation temperature is the temperature at which 50% of the material would be in the form of a solid. So as you start going to higher and higher condensation temperatures, these are more likely to condense out and not be in the gas phase. As you get to lower condensation temperatures, the odds are that they're probably going to be more likely in the gas phase and not as likely to be in the solid phase. But of course, carbon and oxygen, they can very easily react with other things. If you're talking about some of these other elements, they could very easily just be independent. But I'm sure a lot of times they actually do react with oxygen as well. So that's why you can see right here there's the iron, the silicon, magnesium, a lot of these condense out. Now aluminum, titanium, calcium, and all these others, they would also be presumably on the dust grains as well, but their overall abundances are lower anyway. So, but magnesium, silicon, iron, these are generally the highest abundances of the the metals, not accounting carbon and oxygen. So because these very easily condense out and they have the highest abundances, this is where most of the dust grains, their composition is going to be composed of them. So some possible compositions, we could have silicates, we could have pyroxene, which is a magnesium iron silicate, or olivine, which is a magnesium iron silicate, just basically in different ratios. This is what some pyroxene and olivine look like here on Earth. Now, of course, in meteors, they would be much, or in dust grains, they would obviously be much, much smaller than that. Oxides, again, would be very common, silicon, magnesium, iron oxides. Carbon solids, graphite, possibly, but very easily these graphites would probably have some hydrogen attached to the ends there. Also, nanodiamonds have been actually seen. Now, it's not really certain where these nanodiamonds came from. It's possible, through collisions, or just possibly, small amounts will be formed. So a lot of these nanodiamonds have actually been seen in meteorites. Hydrocarbons in the form of PAHs. Again, we'll talk a little bit more about that. Carbides, since we got a lot of carbon up there, you generally form carbide. Silicon carbide is going to be a fairly common one. And then you could also have things like metallic iron, and a lot of these things have been seen in individual meteorites. And like I said, other elements can be there as well, but they're overall less abundant. These are the major players going on here. So some ways we can actually study these grains is that sometimes they're actually seen in meteorites from before the solar system was actually born here. Now, how do we actually identify which grains are presolar and which are just regular old dust caused by asteroids and comets bumping into one another? Well, you get your nice meteorite, which which lands here on the Earth, and you just look at the different grains and you identify them by the anomalous isotopic composition. So everything that's in our solar system has a fairly constant composition, but if you go and find a grain that has a higher quantity of or lower quantity of, let's say, carbon-13 or one of the silicon isotopes or one of the iron isotopes or aluminum isotopes or whatever, in those kind of cases you can say, well, this is anomalous, therefore this must have originated in interstellar space and not in what was eventually our our solar system. So that's what they basically look like. Now here, these presolar, these were basically formed in outflows from stars with different isotopic compositions. So we like to think our solar system is representative of every other solar system in the universe, but in reality there can be different isotopic compositions based upon which solar system you're actually in. Now, the most abundant place to find these presolar grains are actually in carbonaceous chondrites. Now, the carbonaceous part here, that means that essentially mostly composed of carbon. And the chondrites, these are grains that haven't been differentiated by melting in the parent body. So essentially, these are just conglomerations of a whole bunch of different particles, but they never got hot enough to melt into one uniform blob. So it's very valuable because you can basically see the grains as they were and then as they collected without actually being modified by mixing with grains from different areas and everything. Now these are actually fairly rare. Only about 4.6% of meteorites are actually in the carbonaceous chondrites classification. And like I said, they're unique because they've undergone the least amount of heating, so that's why they're pretty valuable. Now, how abundant are the different types of minerals and stuff that you basically find in there? Well, basically you have amorphous silicates. These are the majority of stuff in there. Also have things like phosphorites, ensantites, against essentially magnesium silicates. They're fairly common. Then you have some diamonds over here as well. They can actually take up a pretty decent chunk of the meteorite here. Silicon carbide, graphite, some spinel, corundum. This is essentially just another form of aluminum oxide right here. Hibonite, another one, but these are fairly small in quantity compared to some of these other ones here. Circumstellar, this just means this would be formed in like the disk, as the solar system was actually forming here. Now, actually, remember we talked here about the extinction curve, and we looked at this little bottom portion right here. This is where the silicates and the CH stretch are over in this area. So that's actually just down at these low wavelengths over here. So these little stretches that are actually going on and bends in this here. Basically, these features are seen in outflows of oxygen-rich stars, but not in carbon-rich stars. Because if you're a carbon-rich star, you're probably going to be forming silicon carbides, and then the oxygen, if it is around, will be reacting with the carbon as well. But over here, since these are oxygen-rich, the silicon are generally going to be reacting with the oxygen, and this is where you get a lot of your silicon oxide stretches, and then the silicon O bends over here as well. Now there is a little feature here which is barely visible, but that's again your CH stretch, and this is actually weaker in dark clouds than it is diffuse clouds, and the reason for that might be that the CH bonds might be destroyed by cosmic rays and then regenerated when these carbonaceous grains are exposed to atomic hydrogen in diffuse clouds. So essentially, what's going on? You get these hydrocarbons, but if there is cosmic rays come along, break it apart, but then they basically just can reform on the grain surfaces there. But then again, once they are kind of on the grain surfaces, they kind of just stick on the grains there. So that's why they're fairly weak there. But in diffuse clouds, they're going to be more in the environment. All right, so I mentioned PAHs, the polyaromatic hydrocarbons. So really what these are essentially nice little honeycombs of a whole bunch of benzene rings. So you could get your very simple anthracene down here to your more complicated coronine, hexa, benzocoronine, circumcoronine. They basically just get larger and larger and larger. Um, now there hasn't been any, as far as I know, identifications of a particular PAH for a particular spectral signature, including the DIBs there. But based upon the spectral features that have been seen, it's believed that about 10 to 15% of carbon may actually be in the form of these PAHs that have at least less than 500 carbon atoms in there. And then we also have to include the possibility of the positive and negative charged cations and anions also as well. And what also makes life more difficult and more interesting is that you can very easily be missing a hydrogen atom over here on the side, or you could have some functional group sticking off on there. You could have an OH or an NH2 or whatever basically sticking off the side of these things. So these can very easily be modified. So these are the general starting point, but just use your imagination to how these can be modified. Now, when I got this figure here, it looked like they're all single bonds, but just put the double bonds in there because again, these are aromatic there. Now, the emissions for these can account for about 20% of the infrared emissions in the galaxy. So these are actually, again, quite abundant in there. And actually, they have been, seen in, in meteorites, but spectroscopically observed in space, not as far as I know. So we have some of the spectral features that are generally seen. And over here, these are these out-of-plane, the CH bends that are actually going on. And we have mono, duo, trio, and quartet. And really, this is just saying like how many neighboring hydrogens you have. So right here we have a duo. Here we have a quartet. Here we have a trio. And then we have the mono, him all by himself. And there's another duo over there. So essentially, by looking at these features, you can kind of get an idea, the abundances of or the possibilities of the different PAHs that you have. So like for this one, we got a lot of monos in here. So, therefore it's possible, we have, more of these features in the PAH. And then, maybe not a lot of quartets. So maybe not a lot, actually like this. But again, a lot of that depends upon the quantum mechanics of your particular molecules that you're talking about. And this is basically where we'll stop it. This is actually just looking at a whole bunch of different galaxies and looking at their infrared emissions. And you can notice that they all have these spectral features in common. And again, these are essentially the same spectral features that we were just seeing over here between 6 to 14 microns. So right here, that's basically around here's your 6 to 14. So that's these spectral features that we're basically seeing, and they're consistent along many different galaxies. So that's why you basically have a large proportion of your carbon in the form of these PAHs that are actually being seen. All right, so anyway, that's the end. So we'll be having our final next week. So what will be on the final, it'll be fairly open-ended. Essentially, it'll just be a multiple choice test, which is going to be on Blackboard, and I'll just give you guys as long as you need to actually take that. So I'll be putting that up sometime next week, and then you'll have till whenever to actually get that done there. So anyway, if you do have any questions or something, please just send me an email. I'll be happy to talk to you. And otherwise, keep washing your hands, stay safe, and see you later.